Okay, our last topic of the day. So we're going to talk about if you have two waves interfering with each other and they have different frequencies, what happens? So let's start off. Let me see. So let's say we have a wave. I'm going to need some place to write. Let's go over here. Okay. So let's have two waves. Our first one, y1, is going to be a sine of k1x minus omega 1t. And we're going to have another wave, which is going to be y2. And it's going to have a slightly different frequency. So if it has a different frequency, it's going to have a different wave number. And we want to see if we interfere these two things, what happens. So what I want to do, just to make our lives a little easier, make the algebra a little easier, let's imagine what happens just at some position in time. Let's just call that x equals 0, for example. Because what we want to do is imagine if you were sitting at some fixed position. Let's think of these as sound waves. And we want to know if I create two sound waves with slightly different pitch, what's it going to sound like? And I'm going to say the position where I'm sitting listening, I'm going to call that x equals 0. Okay. The other thing I'm going to do is to make my life a little easier, I'm going to write that this frequency of wave 1, I'm going to say it's some frequency omega plus some delta omega over 2, and that omega 2 is some omega minus delta omega over 2. What? Oh? So you can see that, let me see, delta omega must be omega 1 minus omega 2. All I'm doing is I'm saying, well, you have two frequencies. One's a little higher by some delta omega. Yes, one's a little higher by some delta omega. One's a little lower by some delta omega. That's just a difference in the frequencies. And the reason I'm doing this is going to make our math a little easier. Okay? So let me rewrite what these things look like. So we have y1 equals, is that x equals 0, sine of negative omega plus delta omega over 2 times t, and y2 is a sine minus omega minus delta omega over 2 times t. Okay. You know what? I'm going to write trig identity up here just for your memory. So remember that sine of a plus b is sine of a cosine of b plus sine of b cosine of a. We're going to use that right here. Okay. Let's do it. Let's see. Let me see. This negative here, I can just pull it out, right? So sine of negative theta is negative sine of theta. I'm going to pull that out right here. I'm going to do the same thing right here. Okay, so let's do it. So we have negative a times sine of omega t cosine of delta omega over 2t plus sine of delta omega over 2t cosine of omega t. Did I drop any parentheses or am I still good? Okay. And let's do the same thing for this guy. So here we have sine of omega t cosine of negative delta omega over 2t plus sine of negative delta omega over 2t cosine of omega t. Okay, if I want to add these two together, I want to do y1 plus y2, because that's really what I'm going to be hearing. Okay, cosine of a negative angle is just cosine of the angle, right? Sine of the negative angle, we just said that that's negative sine of the angle. So, can I pull this outside? Okay, so now if I add these, you see that these two terms are equal and opposite. So they're going to go to 0. These two terms are identical. So we're going to get minus 2a sine omega t cosine delta omega over 2t. And that term went away. Okay, I'm going to need to rewrite this over here because I want to talk about that a bit more. Whoa. Ah, okay. Behave. Okay, so what the heck does this look like? So it looks like now we have a sine and a cosine term that have different arguments. I'm going to rewrite that again right here. Okay, so we have y1 plus y2 Okay, so here we have a term that's oscillating pretty quickly at a frequency omega. This is a fast oscillation. This thing, it's oscillating at a much slower frequency. It's oscillating at a frequency that goes as the difference between omega 1 and omega 2. So that's much, much slower. So this is like a slow, let's call it an envelope. So what we have here is if now we plot y as a function of time, what we're going to get is we're going to have this slow envelope. This thing is oscillating at a frequency delta omega over 2. Sorry, let me not draw this right here. This is going to be right here. Okay.
Shouldn't it start at a maximum?
Oh my gosh. Thank you. Is that better? Thank you. Okay, so we do start at maximum because it's a cosine. Okay, so this is our slow envelope. That's this cosine term. Now we have this fast oscillation. So what that looks like, okay? So what this means is if you were standing here and listening to it, you would hear something at the frequency omega. But what you would hear is that the sound would get louder, softer, louder, softer, louder, softer.